Let's continue with linear contrast enhancement. And I will begin this video with a method called piecewise linear contrast stretch. Basically, the difference between this method and the linear contrast stretch I introduced in the last video is that for piecewise linear contrast stretch, we use multiple linear functions to stretch the histogram of the image. Okay, so firstly, I still want to show you this figure here. So X, again, the horizontal axis is for input image, right? The brightness value of input image. Y-axis is for the brightness value of output image. So originally, the input image, its dynamic range is from Bmin to Bmax. It's a relatively narrow range, right? And for the output image, after the enhancement, this is what we want. The dynamic range should be from 0 to 255. So obviously, the output range from 0 to 255 is wider than the input dynamic range, which is from Bmin to Bmax. Okay, so this is the purpose. So how to use piecewise linear contrast stretch? Here it is. So like I said, we have three linear function here, three segments. So at the bottom left, this is the first segment. Okay, and then we have the second segment and the third segment. And you can say three functions, three segments, they are applied to pixels with different values. So the first function is applied to pixels with values from 0 to this specific value. I do not know the specific value here, but you can consider this part of the image. Pixels with values from 0 to this specific value, they are stretched, they are enhanced by the first segment function. And similarly, some other pixels within this range from this let's get back a little bit, from here to here. Let me draw it. Okay, from 0. So these two red lines, they are boundaries for pixels that are enhanced by the first segment. Okay, and then let me change the color of the pen. Other pixels with value from here to here. Okay. Pixels with values within this green range, they are enhanced by the second segment. Similarly, we have the third segment here, right? So say blue pixels. So pixels with values from here, okay, to 255, they are enhanced by the third segment. So this is why this method is called piecewise linear contrast stretch. Okay, because my drawing is very bad, so you should know that this red line and green line, they should overlap with each other. This green line and blue lines, these two lines, they should overlap with each other, okay? And all those lines I just drew, they should be perpendicular to the horizontal axis, okay? And again, just like this figure, horizontal axis is for BV in, or pixel values for input image, and the BV out. The vertical axis is for pixel values of output image. Let me erase them. Okay, let me clean them. Okay, let's zoom a little bit. Let's focus on the first segment of this piecewise linear contrast stretch. Let me turn off the eraser. Okay, so what did this segment do? Did it enhance the image, or did it make those pixels even worse? Okay, so The red dash line here is the input range, okay, for those pixels within this value range, right? And it's horizontal, okay, because X is for input image pixel values, right? So this is the input range. But where is the output range? Y is for output range. So you can say this vertical dash line here is for output range. If you compare input range and output range is even narrower than input range. What does it mean? It means that these pixels used to be distributed within this wide range, but after this so-called enhancement, they're actually having more similar values because their pixel values are distributed within this narrower output range. So actually, these pixels, they are compressed in terms of their values. So for this part, for the first segment, what it did is actually making the situation worse. Those pixels within this range, within this input range, they're even more difficult to identify in the output image. You would ask, why would I do that? There are reasons. Sometimes we just want to make sure that some pixels, if they are not important, we want to just compress their values. So because they are not important, we don't want to focus on them. So it's okay. They cannot be easily identified in the image. Actually, if you compress them, it would be easier for you to identify those pixels are more important. That's the purpose for the second segment. Okay, for the second segment, let me use this pointer again, this pen again. For the second segment, this is the input range, right? Between these two blue lines, right? It's relatively narrow, right? This is the input range. This is the input range for the second segment. But where is the output range for the second segment? It's right here. From here to here. So this is the output range. If you compare the length of blue range and the green range, obviously the green range is wider. So for the second segment, what it did is what? Is enhancement on those pixels within this BV in range. Okay, so the second segment here is to enhance those pixels within the input range. So similarly, what is the third segment is trying to do here? You just need to compare the length of input range and output range. So again, let me erase all the drawing here. Okay, so the red dashed line here is the input range of those pixels enhanced by the second segment, second linear function. And again, this vertical dashed line is for the output range of pixels enhanced by the second segment. Similarly, okay, if we compare second segment and the first segment here, the first linear function here is to compress, is to apply compression on those pixels. So second segment here is actually to do the enhancement. So how about the third one? The third one is also here for compression. Okay? Okay. So here is an example. This is the image I showed you before, and I can provide more information here. So here we have a river. We have a river here. It's called Savannah River. And it's a huge one, so you can say the image between these two green lines, the part of the image between these two green lines is a river. Okay, the left part, this is land. The dark part here is also another land. But here we can say there is another creek emerging, not emerging, merging into the Savannah River. It has a name. It's called 4 Mile Creek. 4 Mile Creek. So let me draw the boundary again. Okay, let me use another river. Okay, another color. So this is another creek. It's called 4 Mile Creek. It is merging into the Savannah River. But you can see that the tone of two rivers is different from each other. For the Savannah River, it's very dark. The colors, all those pixels for Savannah River is dark. But for other pixels that are for the 4 Mile Creek, they are brighter. I can tell you that this image is from a thermal band, which means the higher the value, the higher the temperature. So it means that this creek, the water in this creek has dramatically higher temperature than the water in the Savannah River. This is very abnormal. Okay, usually it means that something is happening in this creek. Okay, it's not likely this is a natural phenomenon. Could be pollution, or could be someone or some factory or some organization. Anyway, someone is charging something into this river to make this river much warmer than the Savannah River. Okay, make this creek much warmer than Savannah River. And you should know that for water body ecology, temperature is very sensitive. It's a very sensitive factor. It dramatically affects all the living things in the river. Okay, so that's another story. I just want to give you a context here. So we have a creek, we have a main river. Now, if I'm asking you to enhance this creek, and I just want to know what is going on in this creek. So I don't care about the land. I don't care about the Savannah River. Can you just emphasize this 4 Mile Creek in this image? You can do that through what? Enhancement. Okay, let me erase the drawing first. Okay, they're here to give you a concept. Okay, so let me turn it off. So this is the result. And this thermal plume, we call it thermal plume because it has much higher temperature than Savannah River. I mean, the water from this creek has much higher temperature than the water in the Savannah River. So we want to emphasize this thermal plume. Okay, so this is the result. Okay, all the land and all those pixels representing Savannah River, they have been masked out, right? They are all white, and only the 4 Mile Creek is enhanced here. And this is what the enhancement do. So firstly, we have this original histogram, right? Please look at this bottom left histogram. So on the left side, this part, this small hill in this histogram, those pixels, they are for land. Okay, and this huge spike is for Savannah, is for pixels in Savannah River. And we can say there are what? Other pixels, they have a relatively higher value, but with low frequency, which means these pixels, they have higher temperature, but not many of them. These pixels, they are for the 4 Mile Creek. So this part of the histogram is the part we want to emphasize. For Savannah River and the land, we don't care about them for now, okay? So this red curve here is the function used by this enhancement. What does it mean? It means that, okay, in general, the pixels for 4 Mile Creek has a brightness value range from 81 to 170. You would ask, how did you get that? That's another story. Okay, you need to, there are other methods in remote sensing. You can mask out the rest of the image and only keep this part of the image available, which is 4 Mile Creek. And then you can check the histogram of this part of the image, so you know the min and max value for 4 Mile Creek pixels. But like I said, that's another story. But let's just assume we know that for this 4 Mile Creek River pixels, the mean value is 81, the max value is 170. So any pixels with a smaller value than 81 will be given 0 in output image, which means the land pixels and pixels for Savannah rivers, they are all 0. I don't care about them anymore. So in the image, they should be totally dark, or say pure black. And any pixel with, oh, sorry, here. Okay. Any pixel smaller than 81, any pixel with a value smaller than 81 is given a value of 255. Okay, so this is output brightness value. Okay, I forgot to mention this. Okay, so that's the reason why those land pixels and Savannah River pixels, they are all pure white in this output image because their value is 255. And the other pixels who has a value larger than 170, they are also given a value of 255. Okay, only pixels for 4 Mile Creek, they are stretched by this linear function, okay? And obviously their dynamic range has been enhanced, because let me show you this again. For this, the 4 Mile Creek River, this is the input range, right? This is the input range from 81 to 170. What is the output range? The output range is from 0 to 255. So because this linear function is right here. Okay, so you can say as a result, land pixels and pixels for Savannah rivers, they are all pure white here, because they are having a value of 255. Okay, they are, in other words, they are masking out. We only care about this 4 Mile Creek, and a linear enhancement was done to what? To enhance the dynamic range of all those pixels for this river. Okay, so this is a very typical but very simple example for piecewise linear contrast stretch. Here, actually, we use 3 functions, right? Although, let me clear them again. So function 1 is a straight line. Function 2 is what? Is this second segment here. Function 3, or segment 3, is again a horizontal straight line. So 3 functions. Okay, piecewise linear contrast stretch. So you could also enhance what? Enhance Havana River. This is the result. So here you can say 4 Mile Creek is not the main character anymore. All those pixels, they are pure black. Okay, so we want to emphasize Savannah River here. Okay, so again, another piecewise linear contrast stretch method has been used, but this time, okay, we only focus on this spike. Like I said, pixels within this spike, they are for Savannah River. Okay, and any pixels outside this input range of Savannah River, they are assigned this time not 255. This time they're all 0, so they're pure black here, right? So segment 1, segment 2, okay, and segment 3, and any pixels not within this part of the image, not within the Savannah River, they are given a value of not 255, 0, 0. And you can say some pixels, they escaped the enhancement here, right? So here we have some pixels, they have non-zero values, and you can consider them as a part of Savannah River. But the most important part is that the land in this image has been mostly filtered out, and this 4-mile creek has been filtered out mostly. Okay, so this is piecewise linear contrast stretch.